PhD and master's here from Albuquerque, and from UNM, and I did it at CHTM as well. I don't have it on my screen. It's on the room computer. Yeah, so I'll just keep talking. Yeah, so I came to CHTM for my grad school. I did both my PhD and my master's from electrical engineering. But CHTM is a center that is located in the South Campus of UNM. And I'll talk more about, a bit more about their research, a very, very brief summary of their research. I did my postdoctoral at the University of Oslo in Norway. I was there for 2.5 years, and then I came back. So I can't ever seem to leave CHTM. So right now I also am a research assistant professor. I also am an adjunct faculty at EC, so I teach courses. But my main job that I enjoy the most is being the NanoFab manager. It is what made me, literally is. I came here to work now. Fit into the CHTM family. They taught me everything I know today. And so I'm very grateful to all of you and to give me a chance to talk. So this is CHTM. It's just a single building, and we are located at 1313 Kudat Southeast. It's in the South Campus. It's what is, in its larger place, it is called as the Science and Technology Park, but for now it's just us. And so it's a facility of about 600,000 square feet. So it's a small building. We are not considered a department, but we are considered as a center because we have faculty and representation from many departments, and I will go through some. And so our core capabilities, just to give a brief overview, this was decided by our faculty in the last faculty meeting. So we started off by, being a center of high technology materials, meaning it just means that anything beyond silicon. Silicon is what exists today in the semiconductor field. And so it is all our chips that is there in our phones, in our computers, they're all made with silicon. But the problem with silicon, the cons of silicon is that it utilizes the characteristics of one material. So what CHTM tries to do, or its inception idea, was that we try to go beyond what is in silicon. So hence the high technology. So we try to work with materials that are made of a composite of 3-5 materials. 3-5, I will keep using that. It just means the 3 and the 5 table of the periodic table, and or the 2 6s, that is in the 2 and the 6 groups of the table. And so this is where the inception of CHTM started. So these were the materials that we started. And CHTM is 40 years old. And so this was years back, was this story. And this is where we are today. And today we have, I'll keep using the word intersectionality or intermingling. We have a lot of departments and we intermingle our research. And that is one of the advantages of CHTM. So we have everything from electronics, photonics, and our magnetic fields and those kind of studies that then intermingles with what we do in fundamental material research. So that comes from the chemistry, the chemical engineering, the material science folks. And then we also have today, we are also looking into quantum technology and quantum science and how AI can help further get better results in our experiments or try to, qualify what we are doing. So we are extending beyond what we had started off 40 years ago. And so this is more of a recent view of it. So just to start off with, I will head backwards and then come back into what we are doing. So as I said, CHTM is 40 years old. We were started in, our inception was in 1983, but I think it was the year before that the legislation of New Mexico gave funding for 5 centers of excellence, and we were one of them. And the reason was the senator at the time fought for us. And so this is the reason why we exist today. And initially, as I said, we started off working on fundamental research and trying to come up with materials that go beyond silicon. So we also work on most of our 40 years of existence. It was not just fundamental research, but applying this into the engineering fields today. So we make devices. And when I mean devices, like electrical devices, like transistors, diodes, but we also have a huge contingency of people who work on optoelectronic devices, such as lasers, LEDs, infrared detectors, sensors. So even though it started off as a place where we do fundamental research, it also grew into a place where we can have startup.
A little bit louder. Just a little bit.
Okay, thank you. Even though we started off as a place for fundamental research, we also extended into a place where it translates into current engineering, into manufacturing, and a place that's an incubator for ideas on startups that would start off companies and stuff like that. So in the past 40 years, we have also had success on that. So some of the images you see here are from many of the I think Albuquerque Journal newspaper and stuff like that that are not existing anymore. And so the figure all the way in the most left-hand corner, is when they actually blasted the site to make this area. But I think initially the idea was to have two conjoined buildings, but we are the only one right now existing. I think there are not. So, but still, research continues at CHTM. And so from here on, I will talk about what we have been doing for the past 40 years. So just like most of UNM, our mission is basically to create an environment to explore. That's just simple part of it. And that is nothing but education. We facilitate an environment for fundamental research and then translating this research into coming up with new ideas and new disruptive technologies. And we also have, sustain a culture of excellence. And I don't want to undermine this problem because, this point, because this is really important because I traveled all around the world with my degree and I realized how good it was and how important the research we did was. And so to say that it is a culture of excellence is just undervalued. And we also promote, of course, as I said, we promote research and education in photonics, in microelectronics, in quantum technologies, in nanoscale materials and devices, and of course, their applications and their integrations into the current technology. We, of course, these are some of our stump speech. So we also foster interactions between the UNM, the education side of it, to federal laboratories like Sandia National Labs, like Los Alamos, and also with industry. And we also promote entrepreneurial spirit because we have had startup companies that have existed within CHTM and have grown on to become big. And then, of course, we educate and try to train the next generation of workforce. And I cannot begin to tell you what a privilege it is to be from that center and then go on to see the next generation coming up, to be the person in between, who has learned from the center and see all these new people with their amazing ideas and, be just a conduit to help them in their journey. It's an amazing privilege. And so one of the most important things of what we do at CHTM, first and foremost, we start off anything with theory, with reading stuff, with research, and that is just nothing but basic part of a fundamental research experiment. So we start off with theories and we then model what we require. We may be modeling a material system. We may be modeling a device or how this device is going to perform. How can we increase its efficiency? So we start off with something fundamental. We model about it and then we apply it to, as we are experimentalists, we apply then to what is happening right now. So we take everything from theory and from modeling and simulation and then we translate it into materials. That is, we do our own material growth. So all these 3-5 materials, 2-6 materials, we grow it within our center. So when I mean growth, it's like plant growth, how a plant grows. That is where we use the word growth. And so it just means creation. And we have many different techniques of creating this. And so depending on what device we are making, let's say if we are making a laser, we will create the material that is required. And then we have the facility, which is the NanoFab facility, which I'm going to talk about, is where we translate what we have created to a device. So that is the part we call as fabrication. So these are words for us that is common, but to people outside, it sounds weird. Like, why are you calling it growth? It just means like plant growth. It's just, yeah. So we have two facilities for the growth of these materials. One is within a CHTM, within our 600,000 square feet building, but we have another one that is called Crystal Growth Building, and that is across the street near the isotopes, the baseball park. It's there, so we have a separate building. It too belongs to UNM. It's just that it is stationed there, and then everything else is within CHTM, including the lab. So going first to the material growth, and so we have two different ways of growing our materials. So the 3-5 materials, that is the ones that come under the 3 and the 5 groups of the periodic table. For example, gallium arsenide, indium phosphide, gallium antimonide. These are just binaries. We have ternaries like gallium indium phosphide, indium antimonide phosphide, those kind of combinations of many of these things. They are done in MBE systems. MBE means molecular beam epitaxy, and this is these materials are grown in high vacuum and at varying temperatures. And we have 4 MBE systems, and the MBE systems are the most expensive equipment we have within CHTM. Our latest one is a Vigo MBE system, and from what I know, it costed about $4 million at the time of purchase. And that was, I think, 10 years back. And so we have these 4 systems, and these are dedicated to growth of 3-5 materials. And we grow many different kinds of 3-5 materials, many combinations of it, but we also have many geometries. For example, we have what are called as quantum wells, quantum dots, dots in a well, dots in a double well, so there's like so many combinations of it. And one of the amazing parts of that was that quantum dots received the Nobel Prize for Chemistry this year in 2023. So I cannot begin to tell you how amazing it was when I heard that news. I walked around the CHTM, and we have posters from our students, who won prizes, and so many of them were on quantum dots. And I was just walking around, and it hit me that, we are working and trying to take that, that what won the Nobel Prize to the next generation. And it was an amazing feeling to be that person who has had some kind of, just having touched it. So amazing. And so our second system is called as MOCVD, which is based in the Crystal Growth Building. And MOCVD is basically means metal organic chemical vapor deposition. It is also another way of growing these materials. So mainly in this system is, there are two MOCVDs in that building. So they basically concentrate on what is called as 2,6 materials, and they are gallium nitride and silicon carbide. Silicon carbide is actually very prevalent right now. Actually, there are many groups who are working on silicon carbide transistors. And from what I know, Intel has invested a lot of their capital on developing silicon carbide technology. And so silicon carbide will become more and more prevalent as we go on. But we also do gallium nitride LEDs. So they grow nanowires, nanopillars, and such. And we also are going into 2D material growth. So at this point, our technology has reached its limit. We already work in atomic limits. Atomic limits means atomic length is the length between 2 atoms in an element. And so basically we have reached that limit. That is the limit at which we work on right now. So where do we go from here? So the only place we can go is take down a dimension. So we work on 2D materials, and examples for that is graphene. Graphene won its Nobel Prize a while back, showing semiconductor behavior in graphene. And so graphene is a 2D material, and the way graphene is done is the one that won Nobel Prize was for its Scotch tape technique. It's just nothing but Scotch tape, just peeling the tape off. And so that's how this 2D material is done. But you have to grow it somehow. And so that is done in what is called as chemical vapor deposition. And then we also have facilities within for material characterization, as in once we grow this material, once we create this material, we have to know if it is the right one, if it is going to work well, does it look good, and so for that we have many different characterization techniques. And some of them are the electron microscope. So we have SEM, we have optical microscopy, we have infrared microscopy, we have these. We also have spectroscopy. And so this is one of our MB systems that's in the MB lab. This is the second MB system. This is the one that I said was the most expensive of all. And so we have a group that is dedicated to it and a research professor who's dedicated just for running the MB system. And this is the MOCVD system that is in the crystal growth. There is a separate group that completely works only on the MOCVD growth and characterization and making devices. And so I will go further. So the last part of the end-to-end integration is actually fabricating the device. So I will talk more about it when we come into our NanoFab slides. And then we also then take what is made into packaging. Packaging is the way we all see a device. For example, if you see the chips that is in our phones, it's already packaged. You can't change it. You can't break it because it's already packaged. And so there are some parts of packaging that we also do just to test if these things work or not. And so for that, we have a few methods. And that is also part of the nanofabrication. We just call it post-fabrication because it's not inside the clean room. It is outside the clean room. And finally, we also have device characterization. So once we make these devices, we have to know if these devices work. And some of these characterization techniques are these. And so this is called as high vacuum temperature probe station measurements. So in these ones, we can start off from 77 Kelvin to go all the way up to room temperature. And so these are probes. So what you can see is that they actually look like needles, but we have to remember that the sizes that we deal with are in microscale and nanoscale. So these needles are made for that sizes. And so we can move them around to make contact with our devices and then measure them at different at different voltages, at different temperatures. So basically at different characteristics, we can measure these. So the next thing we also have is photoluminescence measurements. And these are extremely important when we have optical devices. So for example, if we have an optical device like an LED, and we say that this LED is going to be a blue LED or a green LED or a red LED, the color comes from its wavelength, the wavelength at which this LED or this material works at. And so to know that it is working at that right wavelength to get the color, we have to first measure it. And so that is done by what is a technique called as photoluminescence. And so we have these vast setups that are set up for these photoluminescence measurements. We also have infrared testing, which is important for infrared detectors. We have optical analysis, profilometry, ellipsometry, and other kind of microscopic and laser spectroscopies that are present within CHTM. So we have about 21 labs. And so each of these labs have many of these setups. And each group is dedicated to a different characteristic or a different part of this whole end-to-end integration. And so going into a very brief look into the research at CHTM, I have to say that I neither have the understanding or the know-how to explain a lot of the research that goes on at CHTM. I'll do my best. My own dissertation was on infrared detectors, but we also have many other groups that are working on it and many new groups working on new disruptive technologies as well. And so this is just a snapshot of who we are. So we have 15 faculty members. They are both tenured and tenure track members. We have 15 research faculties and 10 postdocs. So the research faculties basically support the tenure track professors and support the research that currently takes place. They may or may not be tenure tracked. And then we of course have postdocs who are temporary, who come and go, but we have about 10 postdocs. We have 12 staff. The staff do both technical and administrative stuff. And so they are permanent UNM employees. Then we have 54 graduate students. We have 16 undergraduate students currently and about 10 high school students. So we have the high school students as interns, basically. And so some of the labs they cannot enter into because if they are below 18, we are not allowed to have them to dangerous places or, you have to follow OSHA rules. But what it gives them is an understanding of a research environment. It helps them, especially people who are focused in STEM fields. It helps them, further their understanding into research, and maybe we can, somehow facilitate their future career in research. So we have some of these high school students. We also do outreach programs during summer. We also do, these training kits and stuff like that at Explorer. So we also do some of these outreach programs, and we have some student science groups that are based within CHTM who do these work as well, including the faculty. We also have these student organizations who do these. And so these are the faculty, and as I said, we have faculty representing different departments, and hence we have students representing different departments. And we have from physics and astronomy, that is from the Pius building, we have Professor Victor Costa, we have Professor Deals, Professor Drake, and Professor Mafi. Professor Mafi was our director of CHTM, but he recently moved. And so we also have Professor Terape and Professor Kirk from chemistry, and we have Professor Jackson from mechanical engineering, and we have from chemical engineering, we have the Professors Han. And so our director of CHTM currently, the acting director is Payman Zerkesha. And so as you can see, many of our faculty are from electrical engineering. I myself am from electrical engineering, but that doesn't stop us from, having these intersectional areas of study. So we have representatives even within electrical engineering from different fields. So Professor Payman Zerkesha is our director. Professor Cavallo, she is our associate director, and Professor Balakrishnan basically is the director of EBSCO in New Mexico, but he also runs the MBE facilities. So Professor Druick was the longest director of CHTM, and he, about 10 years back, I think he retired. Now he's like completely going away. And we have Professor Husani, who is one of our newest associate professors. We have Professor Fizel. His group basically runs the crystal growth building and do the MOCVD groups, and they work on Reddit. And then we have Professor Osinski's lab. They basically work on nanobio stuff. And we have our newest faculty, that is Professor Goodwin, and she just started. And she will most probably be working on a 3D printer, and she will be working on 2D materials. So this is basically the breakup of the faculty. And this was this old picture I found in the New Mexico Forum from 1987, which was of Professor Bruick. He was our longest serving director. And so this is from Professor Costa's lab. So as I said, is there a question?
We can answer it now or at the end.
Okay. So this is Professor Costa's lab, and he sent me a perfect slide of summary. So basically what they work on is they study these nitrogen vacancies. They call it NV. So they do these NV vacancies in diamonds, and they use that as sensors. And they use it in biological systems. They use these sensors in chemical systems. So this is part of what they work. So of course I'm just explaining the very, very fundamental of it. And you can see here that they have, it is a much bigger field than I can explain it. But they are also, they just won a grant. So they're actually looking for PhD students and postdocs. So they're growing in number. And this is the MBE facility that I talked about. And the MBE facility is within the CHTM building. And so it is a state-of-the-art facility. As I said, we have 4 MBEs. One of the MBEs is being given out as a long-term rent to AFR. So basically that was a very old MBE that was brought in by one of our erstwhile professors from Bell Labs. Actually, when he left Bell Labs, he brought it with him. But it was in such a bad state. It was, after using, it was just sitting there. So AFRL actually spent a lot of money bringing it back to life. They spent they invested a lot of funds into bringing it back to life, and it has a bismuth source, so it is kind of given just for them, and so they use it. And so I can't tell you what other research that goes on there. It's a lot of hush hush. So, but the other MBEs are basically handled by Professor Balakrishnan's group, and his research professor is Tom Rotter. And between them, they train students on these MBE systems. It takes years to be well proficient in MBE growth. And so it is a skill that very small number of people have. So if you are interested, people who are listening to me are interested in doing these growth, please do contact them, because there are only a few people in the world who do it, and so that skill is important. But as I said, it takes years. It takes 4 years. It takes all of your PhD just to learn how to use these tools and to get really good growth out of it. It's not just pressing buttons, but we have to get what we have designed it for, right? So that takes time and understanding and knowing the fundamentals. And so the MBE system is also, they also do have clients where they grow stuff for example, ASU, Arizona State University, sends designs for them to be grown, so we charge them for it. So it is a separate facility from the NanoFab. The NanoFab user list is completely different and our charges are different. And the MBE is a completely different unit as is, where they charge. And so they grow anything, as I said, from quantum dots to quantum wells. So, but the group itself focuses on indium arsenide quantum dots and wells, and they're based on lasers that are called as edge emitters. So these kind of lasers are called edge emitters. And then they have these photonic crystals and single photon emitters. They also do 3-5, or here SB means antimony. So 3 antimony based lasers. They do mid-wave and long-wave detectors. These are IR detectors. For example, mid-wave is very important because mid-wave is how we as human beings or as living beings project. So if you look at a night vision goggle, the wavelength that you are seeing is called as mid-wave. So it's very important to do that. Long wave and very long wave is used for space applications, where they do deep space imaging. So that's what these IR detectors are used for. So they also work on this, and so they also work on solar cells. So 3-5 based solar cells as well. So this is the focus of their group. And then we have Professor Cavallo's group here, and Professor Cavallo's group basically works on 2D materials. They do a lot of fabrication on very complicated surfaces. They have these called as crinkle systems. They have cylindrical systems that they work on, and they're all applications are in terahertz radiation sensors. They have it for sensing, for quantum computing. So it has many large applications. And 2D materials itself is up and coming, as I said. And so the applications of 2D materials can be in transistors, for sensors, for biosensors and stuff like that. The other reason is also a lot of these 2D materials are based on organics. And because of that, they are also can be used as RFIDs. RFIDs are where we talk about things that can be implanted into your skin and can be used for identity things, or for, you can have all your money loaded on a chip and then just scan it when you go out. So those kind of things as well. So they all have to be biocompatible. So it's much easier with 3-5 materials, they can be toxic to human beings. So the reason why people also invest a lot of money on organic based devices is because they can be biocompatible. And so these are some of the varying research that takes place. I didn't go through so many of the professors, but that is a whole talk in itself. I'm here to represent the NanoFab facility, so I would like to talk more about the NanoFab facility. And so the reason why I started off this is just the completing slide. So in case anybody is interested about the grants that CHTM has right now, and I think CHTM at this point has about 300 PhDs and graduates. And so we are growing as we speak. And we also have been winning grants. And so I think it has been pretty successful until now for just a faculty of 15 people. And so it's a faculty of 15 people who have done this much. So just comparing that, yeah, it has been amazingly successful. So I'll come back to what I came here to talk about, and that was the UNM NanoFab. So when I first talked to the rainforest team, I was pretty much panicking because the NanoFab basically runs on its own revenue, and we have our own pool of users. And after COVID, especially when we had to shut everything down for a year and a half, we lost a lot of users. And mainly our large number of users are companies that were working with us. And so a lot of these startup companies basically either closed up or they moved to other places like California or Arizona. And so because of that, our NanoFab lost users. And so I was pretty much panicking as we were losing the last set of our industries that were leaving. And we at this point have almost zero people from industries, just only the academics and the students from UNM are the ones who are in the NanoFab right now. And so we are trying to talk to more people and trying to have more companies come back to do their at least fundamental research or develop their devices within the NanoFab. And hence this push for trying to talk to people whom I usually wouldn't interact. And so this is the NanoFab facility. So simply to put, what do? As I said, we do device fabrication. So what you see on your on this side is that I always get confused. On the right hand side is a material that is grown, and we call this as monolayer growth. So what it means that each of this layer is a different set of 3-5 materials. So let's say this is indium arsenide, gallium arsenide, and they are grown alternatively. And each of them is a monolayer. A monolayer means it's in angstroms. So it's the distance between two atoms, which is called as the atomic length or lattice constant, and that is in angstroms. And so that is basically how small these are. And the only way to image it is by a technique called as TEM. And so that is the only way we can see this. And we could grow it alternately. So that was so some of these images are from my own dissertation. So this was from my dissertation. So we take something like this that is grown in an MBE, and it is grown on wafers. So that's why it looks like wafers. And then we fabricate devices. So in the end, it gets to look like that, nice and pretty. And then we basically dice it into single small chips, and they go into our phones and computers. That's pretty much it. And so this is how it looks like in the end. So some of them are on silicon. We have silicon-based technology as well. We have other kinds of 3-5 material substrates. We have sapphire substrates. We also have organic substrates, which are bendable, so those flexible substrates. So we have different kinds of technology here. And so this is just an image, infrared detector image from my own dissertation again. Originally, if it would play well, it actually moves. It's a video image, but yes, it's PowerPoint, and it either enables sometimes or disables. But anyway, so this is how end product looks like. This is the end product we are trying to gain. And the example here I'm giving is an infrared detector. We of course work on lasers and LEDs and others. And so this is just some of the steps to give you an idea of what we mean by fabrication. So we start off with what is called as mesa etching or etching. Etching simply means removing material. So, but it is the way we put down the shape, the size of the device that we require. Here you can see it has a square shape, and it is a 3D, right? And so it also has a height and all of these things. And this is done by special machines because, of course, we do 3-5 materials. They can be carcinogenic because we have, for example, gallium arsenide. Arsenic is dangerous. So we have to have systems that not only etch it, but is able to clean it up. It's able to, that is able to remove it and make it inert. So we do these. So this is usually the first step in device fabrication, where we lay down a design and we establish the shape and size of our device. So the next step is what is called as putting a insulator that is basically trying to remove the amount of space that is exposed. So we are trying to inert the most of the surface. And we only open up places that we require for it to be contacted. Contacted means it is the way a device talks to the outside. And we usually have metals like gold and platinum and stuff like that, which are very good conductors. We use them as the one that talks to the outside. So we lay out this metal. So this is called as contact metal deposition. And so a metal like gold is laid on here. And then the next step is that we then Usually is the final step, but this is for my infrared detectors. So we have to put in extra metals because it's called as indium deposition, because once this IR detector is made, the IR detector needs to talk to a circuit. And so it has to be bonded onto a circuit. And this circuit could be something for imaging or for video. So it could be very simple silicon circuit, or it could be a very complicated silicon circuit. So once this is made, so that is where I call as post fabrication. This basically gets then included onto or it is called as bonding process. And so it basically gets bonded onto a RFID chip or to a PCB board or whatever we require. So this is basically a very simple introduction to what a fabrication process is. And so this is our clean room. Our clean room is very small. It has 4 bays, and it is about 4,000 square feet, and it is encompassed within the CHTM building. Usually clean rooms are much larger, and they are usually a separate building of its own, because that way then you can keep it at the right temperature, the right humidity, and so the whole building is usually controlled. But here this is encompassed within the CHTM, and we have a mezzanine level that is between the false roof we have and the actual roof we have, and that is where we have all our chillers and scrubbers, which basically cleans the air in the clean room. So in simple terms, clean room just means a lab that is more cleaner than usual. And we keep a particle count. So ours is a class 1000, class 100 clean room. So 1000 means 1000 particles per unit, ppm, or class 100 is 100 particles per ppm. So we control the particle count within this clean room, and hence it's called as clean. And the reason for this is that we work on nano or micro scale materials, and a nanoscale material is a nanoscale device is smaller than a single thread of hair. So if any skin cells or anything falls onto it, it's detrimental for the device fabrication. The device pretty much doesn't work if you have particles. And so because of that, we control it. And the other thing we also control is the humidity and the temperature within the clean room, because this also can be detrimental when we are doing device fabrication. So we have these 4 bays, and our last bay is actually the first bay where we start doing the patterning. That is where we lay down the design. And hence that bay is kept more cleaner than all the other bays. And that is the bay here that is colored in yellow. We call it a yellow bay because we usually use what is called as a photoresist to lay down the patterns. And photoresist is this organic polymer which reacts to white light. So it's very sensitive to white light, and hence we keep it in yellow. And so usually it reacts, basically each photoresist is made to react to a certain wavelength. The photoresist we use basically react to UV. Either ways, we keep that room as in yellow. So people usually lovingly call that bay as yellow bay, just because it completely looks yellow. And when kids come to see, visit CHTM or visit the nano lab, they love looking at that room because everything looks yellow. Everything is glowing in yellow. So it's amazing. Yeah. So this is our entry point where we have this gowning area. The gowning area is the transition area from outside world to inside the clean room. So this is where we divest of all our outside clothes. I mean, not completely, but then we wear the bunny suits. And so this is what we call as a full bunny suit. And that means that we also wear hoods and boots. So there are some clean rooms which do not require such a full gowning thing. They either allow you to wear hairnets, or they allow you to just wear those booties. But we do the full, because we have the whole point in our clean room is contamination. We are trying to minimize as much contamination as possible. The reason for it is also because we have groups who have various different kinds of experiment. And so because of that, because everybody works together, it's not like Intel where you work on only one thing. There are people who work on many different things. So everybody complains about some contamination. So because of that, we try to minimize this, contamination. And the contamination could be just, some kind of organic material that is sitting next to them, some carbon-based material. And that may be detrimental for their device. So because we have these varied number of groups from varied number of departments, we have to be more careful. And so that is part of our clean room. So we wear this full gown and we walk when we enter the bay 1, which is a class 1000. And so this is basically the inside part of our clean room. And so in the bay 1, we have what are called as ICPs, and they are used for etching. ICP means inductively coupled plasma. We have 2 of them. One is with chlorine chemistry and one is with fluorine chemistry. We have, this is for laying insulators like silicon dioxide and silicon nitrides. So this is called as a CHA evaporator, and we have many different crystals here. For example, we have aluminum oxide, we have silicon dioxide, we have silicon nitride and stuff. So this is basically very simple. You just buy these crystals from the company and then you just evaporate it onto your material. The last thing that we have on this bay, on this side of the bay, is PECVD, and this one contains the most dangerous gases that is there in our clean room. It has ammonia and xylene. And so these are one of the more dangerous gases. This one, we deposit silicon nitride at high temperatures. And the reason for that is that if the silicon nitride growth is bad, it actually peels like bad skin, or how a snake sheds its skin. It basically just comes off your surface. So if it is not a good deposition, then it won't stick well. It just basically comes off. Then your whole device is not working. And so the other thing that we have here is also we have this glove box, and this is where organic materials are done. For example, polymers and graphene materials. So anything that has carbon in it is used in this glove box. So it's like a clean room within the clean room. And then we also have high temperature furnaces. This is to heat up our devices, or make the devices work at high temperature. This one works at 1500 Celsius. So it goes very high. So 1500 Celsius. And so this is the highest going furnace that we have right now. This is the next bay. And here we have what is called as an asher or an etcher unit. This is to etch metal. The other etchants that we had was just etching 3,5 materials or 2,6 materials. This one is specifically to etch metal. So it removes metal. So the chemistry in this is different from the others. And then we have these tools. These are called as contact deposition tools. So this is a metal evaporator, and this is in which we, for example, evaporate or put down our gold or platinum or these kind of materials. And so this is done at high vacuum. And so we also have a thermal evaporator, which is high vacuum and high temperature. And so this one is kind of our, the other one is our workhorse. The previous one that I showed, so we do all precious metals like gold and platinum and stuff. I'll use again the word contamination. So to reduce contamination, the ones that are more sticky like aluminium and indium, which just stick to everything, is done on this one. So again, it is to, minimize contamination. I'll keep using that word. It's what is our main goal. So the whole reason of having a clean room is to reduce contamination. So this is our acid and base bay. This is the final bay that is a class 1000. And so here is where we do all our etchings. We use acids and bases. And so everything that is done here is collected in canisters, and then it is not put down the drain. It doesn't go back into the waste of the city. It is collected separately, and we have separate ways of disposing of these materials. So basically, it is done by the EHS department at UNM. So UNM basically collects our chemical waste, and so we don't everything that is collected that we have, that we clean it, and we clean it so well that it is filtered so well that we can give it back to the city of Albuquerque. So we are completely environmentally friendly as well. So everything else is collected as hazard waste. And so this bay is also where we are going to expand more the previous bay, because we got a grant for buying a new lithography tool. And so within the next 2 years, this is where this bay will expand to. And we are hoping we will have more users come in once we get a new tool. And so, So this is our final bay, which is the class 1000. And this is the yellow bay that everybody talks about and are fascinated by it. So this is the class 100 bay. So it's much more cleaner than all the rest of the bays. And so I'll just try to wrap this up. So these are the post fabrication work, and this is not inside the clean room. It is outside the clean room, and this is where we can dice them into small pieces. We can polish them. We can also do what is called as wire bonding, which is basically connecting wires to the devices to a PCB board. So that's basically what we do here. And so we also have these many characterization tools. This is our electron microscopy tool. This is our XRD tool. That is the one where we do X-ray diffraction measurements. Then we have MPMS tool, which does measurements in magnetic fields. Then we have a spectrophotometer, which basically we do transmission measurements and in different wavelengths. Then we also have FTIR tools, which we work on infrared measurements. So just to wrap this up, so this is the rates for the NanoFab and the service center. We call it NanoFab and service center because everything inside the clean room, everything outside, like the characterization tools, are called as the service center. So the service center, of course, is growing because we also have, as I said, we have this new tool coming in because of the grant. We also have a new bonding tool coming in, which will be outside. And we also have the 3D printer tool, which is here, but it's not yet installed. So once the 3D printer is up and running, and it's going to be a metal 3D printer, which is very unique. Usually 3D printers just use bio or polymers. They make these flexible stuff, but this is going to be a metal 3D printer. So it's going to be used for fundamental research. So that also will come under the service center. And we haven't decided the rates yet because we haven't started it. So right now the rates are for UNM, for within the UNM, it is $66 per hour, and it reaches a cap at 600. And so everything comes under it, like the SEM, everything comes under that, that block price. But if you're using each, you don't want to use the clean room and you want to just use one tool, it's $88 per hour. And for anybody external, we don't separate between Los Alamos, Sandia, or industry. It's one price, and that is usually $250 or $251 to be just different. Assisted academic means if I or one of our technicians or somebody else helps you with it, then we charge $250. If not, usually we just train the students. They are trained for the next 4 years, or like me, been trained I've been there for 11 years now. So, and so this is the current team. Douglas is the magician who keeps our old clean room running. Everything we have was either donated or we got it from somebody else. So none of them have any servicing, because even the company stopped making it. And so Douglas basically keeps these things running. And he was the one who trained me when I started off as a graduate student. So yes, everything I have learned it from Douglas. And our new hire now is Dr. Emma Renteria. She's also from CHTM, and so she'll be joining us as a permanent staff. So again, she's also good at developing new recipes or new processes. So she also will be training students. So if such a thing happens, then they are charged $250. That means that they're developing a new process and they need help from somebody who is trained or somebody who has, the technological know-how. If not, we don't charge that. So Dr. Ali is just a temp right now. And then we have interns. So our wonderful interns, we have Alex, Kayla, and Gabriel. They are all UNM students, and they are just our part-time interns who work maybe 7 to 10 hours per week. And Akanksha, Angela, and Saukya are students from Ames High School, and they're just our high school interns, and they just pretty much manage our clean room stores, where we have a store where we give away the face masks or tweezers or, some of the things you require. So we sell that to them. And so we cannot allow the 3 of them to enter into the clean room because they're 17 years old. So that is the reason why they're only present in the stores. But it still gives them a chance and opportunity to, deal with all the researchers there, ask questions when they walk into the store. And yeah, so we try to. So just wrapping it all up, what we look at CHTM is basically a human endeavor, to explore, to satisfy our curiosities, to give people the wings, to give them the chance, the environment to grow themselves. And in basically in terms, we just try to create more and more disruptive technologies. It's simple to say disruptive technologies, more harder to envision and implement it. And this is something that our director always says, we hope to leave this earth better than we found it. So that's just basically wrapping up. Thank you so much.
There were 2 questions online. One Or maybe comments, I don't know. One says any novel materials developed for the application of hydrogen production and process as in applications for hydrogen-based electric vehicle and renewable energy systems.
No, for now we don't do hydrogen-based renewable EVs. We don't.
And
I would suggest that person to talk to mechanical engineering. They do have a large contingency. They usually have that race car that races. They do the racing.
And then they said, I can see that this microfabrication facility and tools are very useful for producing novel photovoltaic cells. I appreciate sharing technologies and ongoing research other than PV that are engaged in renewable energy field. Thank you.
Do you have any questions?
What's a disruptive technology?
Yeah, it basically is something that challenges the existing system. So the existing system today in semiconductor field is silicon. Silicon has existed more than 60 years. Ever since it was the first material that showed semiconducting behavior. So semiconducting basically means a device or a material that is neither a conductor like a metal, nor an insulator like plastic, or like the sole of my shoe that is an insulator. And so semiconducting material is somewhere in between. And so silicon was the first one to be discovered as that. So that became the existing technology. Everything, all the fabrication facilities in the world, from Intel to IBM to everybody else, have these fabrication facilities based on silicon, only on silicon. So everything is based on silicon. All their machines are made specifically to work on silicon. They are made for large scale manufacturing for silicon. So everything they use there is for silicon. So we can say that we are disrupting, as I'm just using NanoFab as an example. And what we are doing is disrupting that concept of silicon, that, hey, with silicon, you're just having, one element, you have just the characteristic of one element. What if I want to do much more than that? What if I want to do much smaller than silicon? What if I want to do much more wavelengths? What if I want to do color devices and stuff like that? So then we need all these different chemicals, which the existing technology doesn't provide. So we are basically a fundamental research facility. And so we are able to have new experiments done. For example, even me for my dissertation, I made a setup. And then after I was finished, I just took it down. So because we are an educational facility, we have the capabilities of doing that, where you can try to, find new ways of doing it. It works or it doesn't work. It's not a big deal for us because that is part of education. So that's why we call it as a disruptive technology, something that doesn't exist, but also kind of questions the existing notions.
The whole new iPhone, everything else, say titanium.
Right. It doesn't really mean much.
I know, what does it mean?
Because now we are trying to go smaller and smaller in size. Maybe in another 10 years, we will have implanted phones. We wouldn't need to carry phones, or, it could be anything. Sky's the limit. We cannot stop by asking questions. We have to always say, why not? Why can't I do this? And that's what most of the students try. So many a times what we are doing is being done for the first time ever. That's also can be called as disruptive.
Are you working on like new, but everybody's trying to get the battery storage, we're all battery. Are you working on that type of new technology?
There are, some of these applications can come into applications of batteries, of memory devices as well. That is something I didn't talk much about, but you can have like memory devices and also power units. Because right now, if you look at our laptops and stuff, they're this huge is because we need such a large power unit to keep it cool. So, we can develop new technologies, new materials that are thermally sensitive, so we can have much smaller cooling units. So if we go much smaller cooling units, we have much smaller devices. So everything is about going small and going better. And the last thing that I also did not talk about is space applications. I only touched about it because of the infrared detectors. So the last Hubble telescope came back and it was repaired and sent back again. And it went with the infrared detector that was made of mercury cadmium telluride. And again, in the infrared detector field, it is the silicon of their field. So that has been the existing technology. So when it came back and it went with the existing technology. So for a person like me who worked on disruptive material, I would like the next time it comes back and gets repaired to go with one of our devices. So again, the reason for it is that it's much better. It can give much, you can image much deeper, you can get better images, you can get videos. To get videos is much more difficult. As you can see, I just showed you an image, but to take a video, you have to have much more complicated. So your device has to be more complicated. That means your material with which you make that device has to be more complicated. So it's all, it's all on a string. Yeah.
No source, really.
The same person just was wondering if there was a specific scientist or professor that they could connect with in mechanical engineering.
In mechanical engineering at CHTM, it's Professor Nathan Jackson. Yeah, but there's also mechanical engineering department, and they can be contacted there as well. And I have to say that we also have a sister facility in mechanical engineering that is a NanoFab, and it's called MTTC, but they solely work on silicon. So they work on MEMS and they work on silicon. So that is a very small facility within the mechanical engineering.
And then he's also asking, thermoelectric materials often are fabricated at nanoscale with special semiconductors. Any research in this field or in general energy harvesting materials?
No, not yet. We don't have that yet. Other than solar cells and stuff, we still don't have much into energy harvesting materials or what goes EV.
Thank you. For the high school students, does CHTM only take high school students from Ames?
No, actually, we used to have students from Highland High School when I graduated 10 years back. So at that time, we had more, more representation. Right now, Ames is the one that's right next to us, so it's much easier to have them. And their chemistry professor is very good, and he usually keeps giving us recommendations of very good students in his classes, like, oh, this person may be good for you, and things. But we would love to. Actually, I interviewed a few people, but they never came back from Highland School and South Valley High School, I think. But yeah, so we would like to expand more. And when we did our Kids at Explorer, we gave out our cards to parents and told them, could you contact your science teacher? So because before COVID, when 10 years back, we used to have field trips where the science teachers would bring their class, even third, fourth graders. They don't have to be high schoolers. Even though in that age they understand. So they used to bring them for field trips, and that's not there anymore. So we gave out cards asking them, could we contact their science teachers, so that we also would have interns from different schools, especially people who usually don't get the chances, for it. And I also remember we had this outreach program to Navajo Tech, and this was again 10 years back. And I remember going to Navajo Tech to do the kits, that basically we show small experiments. And so,
Leo in high school would be a good place to recruit because it has a lot of the Native American and
and I remember
Hispanic.
at the time, there were students who were like, oh, this is so far beyond. And I told them, if I can do it, you can do it. So it's basically trying to show them that we are here, we are represented. Just come in and look at us for a moment.
Is it transportation? Because that's an issue.
Yeah, but all of these things we can get funding for. We can still apply funding from UNM. But we have to have the participation from ground up. We have to have cooperation from their teachers, from their parents, from their community as well.
All right, I think we're out of time. Thank
Okay.
you very
Thank
much.
you.